The cosmos began in a flash of light and energy, but what if that iconic moment was not the true beginning? What if the universe slipped into existence through a back door in reality itself? That back door is called quantum tunneling, a bizarre rule of the quantum world where particles vanish and reappear as if by magic, crossing barriers they should never overcome. Could this very phenomenon be the secret architect of our entire cosmic story? In the next few minutes, you will gain a front row seat to 30 of the most incredible ideas in modern physics, theories that attempt to solve the ultimate mystery. We will explore how a universe might tunnel into being from absolute nothingness, how black holes could give birth to new realities, and whether time itself is a quantum accident. The answers will reshape everything you think you know about existence. What does it truly mean for something to come from nothing? Our journey begins with the simplest and most profound question of all. How did everything begin? The first theory provides a startling answer. It suggests our universe did not explode into being. It emerged. It appeared quietly and completely from a state of absolute nothing. This is the theory of tunneling from nothing, championed by physicists like Alexander Vilenkin. To understand this, we must first redefine what we mean by nothing. In physics, true nothing is not an empty box. It is not a dark, silent void waiting to be filled. It is something far more subtle. It is a state of perfect balance where all forces cancel out, leaving a total energy of precisely zero. This is the quantum vacuum, and it is not empty. It is a seething sea of potential where particles and energy flicker in and out of existence on borrowed time, following the bizarre rules of quantum uncertainty. In this quantum nothingness, anything can happen for a fleeting instant. The theory proposes that our entire cosmos was one of these fleeting instants. A quantum fluctuation on the grandest possible scale, but there is a problem. To go from this zero-energy state to a rapidly expanding, energetic universe, you must cross a barrier. Think of a ball resting in a deep valley with a towering hill on one side. To get to the lush landscape beyond the hill, the ball needs a tremendous push, an infusion of energy it simply does not possess. Classical physics says it is trapped forever. Quantum mechanics, however, whispers a different story. It says there is a chance, however small, that the ball could simply vanish from the valley and reappear on the other side of the hill without ever climbing over it. This is quantum tunneling. In the beginning, our universe was that ball in the valley of nothing. The hill was a barrier of potential energy, and through a cosmic scale quantum tunnel, it appeared on the other side, bursting into the inflationary expansion that set everything in motion. One moment, there was only the silent hum of quantum potential. The next, an entire universe had tunneled into reality, born from a probability. But if the universe tunneled from nothing, what exactly did it tunnel from? The second theory offers a breathtaking vision that redefines the very meaning of beginning. It is called the Hartle-Hawking no-boundary proposal. This idea, born from the quest to unite quantum mechanics with gravity, suggests our cosmos did not have a sharp, singular start like the bang of a firecracker. Instead, it proposes the universe has no boundary in time, no edge where you could point and say, this is where it all began. To grasp this, picture time not as a straight line stretching back to a starting point, but as a dimension that gently bends and transforms. In our everyday experience, time is distinct from the three dimensions of space. We move through it in one direction. But the Hartle-Hawking theory imagines that if you could rewind the cosmic clock to the very earliest moments, the familiar arrow of time would soften, curve, and ultimately become more like another dimension of space. Think of the Earth. If you start at the North Pole and travel south, your journey has a clear beginning. But the surface of the Earth itself has no edge, no boundary at the North Pole. It is just another point on a smooth, continuous sphere. The no-boundary proposal suggests the entire history of the universe is like the surface of a globe, but with 4 dimensions instead of 2. In this picture, asking what happened before the Big Bang is like asking what is north of the North Pole. The question loses its meaning because there is no before, only a smooth, finite geometry that includes all of reality. So, how does this connect to our story of quantum tunneling? In this framework, the universe's initial state is not a point of infinite density, but this smooth, compact, timeless geometry. The transition from that state to the expanding, time-filled cosmos we live in is not a violent explosion. It is a quantum leap, the mathematics of the universe's wave function, which describes all its possible states, shows a high probability for tunneling from that no-boundary condition into a classical, expanding universe. In essence, our entire reality quantum-tunneled not from nothing, but from a state where time as we know it did not yet exist. It emerged from a geometry without a past, a self-contained origin story written in the fabric of space-time itself. The smooth geometry of a no-boundary origin is elegant, but it leaves a haunting question unanswered. What lies beyond that geometry? The third theory dares to propose there is a beyond. It suggests our universe is not a solitary creation, but a bubble in a frothing, infinite sea. This is the idea of a quantum fluctuation within a pre-existing meta-universe. Picture an ocean, vast and eternal, its surface not made of water, but of the fundamental fields of reality. This is the meta-universe, a parent cosmos that may have always existed, governed by its own, possibly unfamiliar laws. In this eternal sea, quantum fluctuations are not rare events, they are the constant churn of existence. Tiny regions of this cosmic ocean can randomly gain or lose energy, wobbling between different possible states like a droplet poised to change form. Most of these wobbles fade instantly, reabsorbed into the background hum. But very, very rarely, a fluctuation does something extraordinary. It finds a path, a quantum tunnel, to a completely different and more stable state of being. Think of it like a pocket of supercooled water in the ocean. It is liquid, but it is desperate to crystallize into ice. All it needs is a tiny nudge, a seed, to trigger a sudden, dramatic phase change. In the meta-universe, that nudge is a quantum tunneling event. A microscopic region, through sheer random chance, tunnels from the meta-universe's vacuum state into a new, lower-energy vacuum. This is not just a particle appearing, it is the birth of an entirely new set of physical laws. And once that new, lower-energy state is reached, something incredible happens. The region undergoes a process called inflation. It does not just expand, it explodes in size, doubling and redoubling in fractions of a second, stretching that microscopic quantum seed into a cosmos billions of light years across. That inflated bubble, with its own distinct laws of physics, its own particles and forces, is our universe. We are living inside one of those rare, crystallized bubbles in the eternal ocean. The implications of this are staggering. If this theory holds, then our Big Bang was not the first, and it will not be the last. In the infinite expanse of the meta-universe, these quantum nucleation events could be happening constantly in an endless cycle of creation. Each bubble universe, born from a random quantum tunnel in the parent cosmos, would inflate into its own isolated reality, forever disconnected from its siblings and its parent. We would be part of a multiverse so vast that every possible variation of physical law, every conceivable arrangement of matter, would exist somewhere in the froth. Our universe, with its perfect balance for life, would not be a miraculous one-off. It would simply be one bubble among an infinite number, a single possibility that happened to tunnel into existence. But how exactly does a microscopic bubble of new reality explode into a cosmos? The fourth theory introduces the architect of that explosion, a mysterious entity known as the inflaton field. This is not a field of grass or flowers, but a field in the physicist's sense, an invisible energy that fills all of space, like the electromagnetic field, but with one unique and powerful property. It is responsible for cosmic inflation, the period of unimaginably rapid expansion that shaped our universe's large-scale structure. To understand its role in our quantum origin story, we need to visualize its energy landscape. Picture a vast, complex terrain of hills and valleys. This landscape does not represent physical space, but represents the possible energy states of the inflattened field. A marble resting in one of the valleys represents the field's current value. The lowest valley is the true vacuum, the most stable, lowest energy state the field can occupy. But at the universe's inception, the inflattened field might not have been in that true vacuum. Instead, it could have been trapped in a false vacuum, a higher energy valley separated from the true vacuum by a towering hill, a potential energy barrier. In this precarious state, the field is metastable. It is like a marble perched in a small dip on a high plateau. It seems stable for a moment, but it is desperate to roll down into the deep canyon far below. Classically, it is stuck. It does not have the energy to climb the small lip of its dip and begin the descent. Quantum mechanics, however, provides a secret escape route. Through quantum tunneling, the inflattened field does not need to climb. In a random quantum event, it can vanish from its false vacuum valley and reappear on the other side of the barrier, in the lower energy valley of the true vacuum. This process is called false vacuum decay. When this tunnel occurs, even in a microscopic region of space, the consequences are cosmic. The difference in energy between the false vacuum and the true vacuum is colossal. And when the inflattened field tunnels to the lower state, all that pent-up energy has to go somewhere. It is released in a cataclysmic flash, flooding the region with an intense, repulsive gravity. This is the trigger for inflation. That tiny, tunneled region does not just expand, it undergoes exponential expansion, doubling in size over and over again in intervals so short they are almost incomprehensible. The energy release smooths out the universe, stretches it flat, and plants the seeds for all future galaxies. So the sequence becomes clear. First, a quantum fluctuation or a no-boundary geometry provides the nascent universe. Then the inflattened field, trapped in a false vacuum, undergoes a quantum tunnel. That tunnel releases the energy that powers the inflationary engine, transforming a quantum seed into the vast, structured cosmos we observe today. The inflattened field was the catalyst, turning a probabilistic quantum event into a classical, expanding reality. The inflattened field's quantum leap from a false vacuum paints a vivid picture, but the mathematics behind such a cosmic transition is where the true magic lies. This brings us to the fifth theory, a journey into the realm of Euclidean instantons. To calculate the probability of the universe tunneling into existence, physicists had to venture beyond our familiar experience of time. In our everyday world, time is a relentless one-way flow. But in the quantum realm, especially when dealing with gravity, the equations become intractable. The solution was a brilliant mathematical trick, a kind of conceptual rotation. Instead of working with real time, physicists switched to imaginary time. This is not time as we feel it pass, but a fourth dimension treated just like the three dimensions of space. This creates what is called Euclidean spacetime, a four-dimensional geometry where the sharp distinction between time and space blurs entirely. In this strange, timeless landscape, the equations of quantum gravity become solvable, and within these solutions we find the instanton. An instanton is not a particle or a physical object. It is a mathematical shape, a specific configuration of the gravitational and inflattened fields that describes a complete, self-contained event in Euclidean spacetime. Think of it as the blueprint for a quantum tunnel. Imagine you need to get from one valley to a lower one, but a massive mountain range separates you. In real time, you would have to find a way over or through. But in the timeless geometry of Euclidean space, there is another path, a smooth, curved tunnel that burrows directly through the mountain, connecting the two valleys without ever going over the top. This tunnel is the instanton. It represents the most probable pathway for the universe's fields to transition from one state to another. The instanton provides a concrete, calculable history for how the universe could have tunneled from nothing or from a meta-universe state into an expanding cosmos. The probability of our universe appearing is then tied to the properties of this instanton, specifically its action, a measure of its energy and duration in this imaginary time framework. A simpler, smoother instanton with a lower action means a higher probability. So the birth of our cosmos becomes less a random accident and more a matter of statistical likelihood, mapped out in the elegant, timeless geometry of imaginary numbers. These mathematical ghosts, these Euclidean instantons, give us the first rigorous calculations for how something as monumental as a universe could quantum tunnel into being, offering a glimpse into the mechanics of creation itself. Euclidean instantons give us a mathematical pathway, but what if that pathway leads not to a single beginning, but to a cycle of endless rebirth? This sixth theory reimagines the origin of our cosmos not as a singular tunnel from nothing, but as the latest turn in an eternal cosmic wheel. It draws its power from a radical approach to quantum gravity known as loop quantum gravity. This framework proposes that space itself is not smooth and continuous, but woven from tiny, indivisible loops, a fabric of space-time quanta. When you rewind our expanding universe in this model, you do not arrive at an infinitely dense, infinitely hot singularity where the laws of physics break down. Instead, as space is compressed to its smallest possible scale, a powerful repulsive force emerges from the quantum nature of gravity itself. This force acts like a cosmic trampoline. Imagine the universe as a balloon being deflated. In the classical Big Bang story, it shrinks to a point of zero size and infinite density. But in loop quantum gravity, as it approaches that extreme, the woven quantum fabric of space resists further crushing. The deflation halts and the universe bounces, beginning to inflate once more. This is the concept of the quantum bounce, where a previous cosmic era collapses, only to rebound into a new expansion. So where does quantum tunneling fit into this cyclical picture? The bounce itself may be a tunneling event. Picture the universe's journey not as a straight line, but as a path over a mountainous landscape. The collapse of the old universe represents a descent into one deep valley. The expansion of the new universe is the ascent out of another. Separating these two valleys is a colossal ridge, a barrier of immense potential energy that would be impossible to cross under normal classical rules. The universe, at its moment of maximum compression, does not have the energy to climb this ridge. Yet we find ourselves in a new, expanding phase. The proposed mechanism is a grand, cosmic-scale quantum tunnel. At the moment of the bounce, when the universe is at its smallest and quantum effects dominate completely, the entire cosmos executes a probabilistic leap. It vanishes from the valley of collapse and reappears in the valley of expansion, having never traversed the impossible mountain in between. This transforms our story from a one-act play into an endless epic. Each cycle, each universe begins with a quantum tunnel from the ashes of its predecessor. The Big Bang was not a beginning, but a transition, a moment of quantum resurrection. In this view, our universe is a phoenix, perpetually rising from its own condensed remains through a loophole in reality, a testament to the universe's incredible ability to reinvent itself. A universe reborn through quantum bounce offers a stunning vision of eternity, yet it cannot answer why our reality feels so peculiarly fine-tuned for existence. This brings us to one of the greatest and most persistent mysteries in all of science, the cosmological constant problem, and the seventh theory that ties it directly to our quantum origin. The cosmological constant is Einstein's term for the energy inherent to empty space, what we now call dark energy. It is the force behind the universe's accelerating expansion. The mystery is not that it exists, but that its value is absurdly, inexplicably small. Quantum field theory predicts that the vacuum of space should be boiling with an enormous density of energy, a value so large it would have ripped the cosmos apart instantly after the Big Bang. Yet observation reveals a value 120 orders of magnitude smaller, a number so tiny it is like comparing the size of a single atom to the entire observable universe. Why is our dark energy so negligible? One compelling answer lies in the marriage of quantum tunneling and string theory. String theory suggests the fundamental ingredients of reality are not point-like particles but vibrating strings. To make the mathematics work, it requires extra dimensions of space, curled up into intricate shapes called Calabi-Yau manifolds. The way these extra dimensions are folded determines the laws of physics in our four-dimensional world, including the value of the cosmological constant. Crucially, there is not just one way to fold them. There are perhaps 10 to the 500 different possible configurations, each corresponding to a different vacuum state, a different universe with its own unique constants. This is the string theory landscape, a vast, mountainous terrain of possible realities, each valley a stable universe with its own set of physical laws. In this landscape, our universe, with its tiny cosmological constant, is one valley among an inconceivable number. The theory proposes that our cosmos did not simply pop into being in this specific valley. It quantum tunneled here, in the primordial quantum foam, or from a preceding meta-universe state, a bubble nucleated. But its journey was not over. It could have tunneled into any one of those countless vacuum states. The process of inflation, driven by the inflattened field, may have involved not just one tunnel, but a cascade of them, a random walk across the landscape of possibilities. Our universe's specific, oddly small value for dark energy was not chosen. It was stumbled upon, the result of a probabilistic quantum leap into a particular low-energy valley. In this view, the fine-tuning we observe is not evidence of design, but a consequence of a cosmic lottery. We live in a universe that tunneled into a habitable vacuum because in a multiverse of infinite possibilities, some tunnels had to lead to conditions where galaxies, stars, and curious minds could eventually arise to wonder about it all. The landscape of string theory offers countless possible homes for a universe, but what if our cosmic home was born in the most extreme environment imaginable? The eighth theory proposes a startling cosmic lineage, that our entire universe is the offspring of a monstrous black hole in a parent cosmos. This idea transforms black holes from ultimate endpoints into cosmic wombs, where the crushing grip of a singularity becomes the cradle for a new reality. At the heart of every black hole lies the singularity, a point where density and gravity become infinite and our known laws of physics cease to function. It is a boundary of ignorance, a one-way door from which nothing, not even light, is supposed to return. Yet, where classical physics sees an end, quantum gravity hints at a possible transformation. The extreme conditions at the singularity are not so different from those at the moment of the Big Bang, an arena where quantum effects dominate and the fabric of space-time itself becomes probabilistic and fuzzy. In this quantum foam at the edge of a singularity, the distinction between a crushing end and an explosive beginning may blur entirely. One speculative pathway is through a white hole, the theoretical time reversal of a black hole. While a black hole's event horizon is a point of no entry, a white hole's horizon would be a point of no exit, violently spewing out matter and energy. Some models suggest that what we perceive as the Big Bang could be the white hole eruption of a black hole singularity from another universe, a tunnel through the quantum gravitational barrier that separates collapse from expansion. Another, even more profound idea suggests the interior of a black hole does not end at the singularity. Instead, through a process of quantum gravitational tunneling, the compressed spacetime within a black hole pinches off and reconnects to form a new, separate region of expanding spacetime. Imagine a narrow, infinitely deep well in the fabric of a parent universe. At the very bottom, where the well should close into a point, quantum effects stitch that point to the beginning of a new inflating bubble. The matter and energy that fell into the black hole in the parent universe would then provide the raw material for the new one, its information and structure scrambled but not destroyed. In this breathtaking scenario, every black hole in our universe could be a potential seed for a new cosmos, a branch in an ever-growing fractal multiverse. Our own universe, with all its galaxies and stars, might then be the interior of a black hole residing in a grander ancestral reality, a cosmic Russian doll of creation born from a quantum tunnel at the edge of infinity. The idea that black holes could be cosmic wombs leads to a breathtaking and intimate possibility. This is the baby universe hypothesis, a theory that reimagines our entire cosmos as part of an infinite branching family tree. It suggests that deep within the heart of a black hole, where gravity warps reality beyond recognition, a new universe can be born, budding off from its parent like a leaf from a stem. To see how this works, we must look at the fabric of space-time not as a static stage, but as a dynamic, elastic sheet. Under normal conditions, this sheet is smooth and continuous. But at the singularity of a black hole, it is stretched and twisted to its absolute limit, creating a region of unimaginable density and quantum chaos. Here, the rules are written by probability. In this seething quantum foam, fluctuations are not just tiny particles appearing and vanishing. They can involve the very structure of space-time itself. One particularly dramatic quantum fluctuation could cause a microscopic region of this intensely warped fabric to pinch off. Think of it like a droplet of water forming on a faucet. The droplet is connected, stretching, until finally the connection severs and it falls away. In the black hole's core, a bubble of space-time, carrying with it a tremendous concentration of energy and information from all the matter that fell in, could perform a similar feat. It pinches off from the parent universe's singularity through a quantum tunnel, a sudden probabilistic leap that severs its causal ties. This new bubble does not remain a tiny knot. The energy within it, perhaps the repulsive force of a quantum bounce or its own inflattened field, triggers a rapid inflationary expansion. In a flash, that pinched-off bubble blossoms into a full-fledged universe with its own dimensions, its own laws of physics potentially different from its parents, and its own arrow of time flowing forward from that moment of separation. It becomes a baby universe forever disconnected from the cosmos that gave it birth. The black hole's event horizon acts as a one-way cosmic membrane, ensuring no signal, no light, no information can ever pass from the child back to the parent. From our perspective inside the parent universe, the black hole simply consumes matter and slowly evaporates. But on the other side of the singularity, an entire new reality has begun its journey. This transforms our view of the cosmos from a solitary entity into a vast genealogy. Every black hole that forms in our universe, from the stellar mass ones to the supermassive giants at galactic centers, could be a potential birth event. Our own universe, with its billions of galaxies, each harboring billions of black holes, would be a staggeringly fertile realm, constantly spawning new cosmic offspring. And if this is true, then a haunting, beautiful question follows. Could our entire universe, with all its history and splendor, be the interior of a black hole residing in a grander, ancestral cosmos? We may be living inside a baby universe, one branch on an infinite, growing tree of reality, where creation is not a singular event but an ongoing process happening in the darkest hearts of collapsed stars. Supersymmetry offers a startlingly elegant vision for the universe's fundamental architecture, and its connection to our quantum origin story is profound. This theoretical framework proposes that every known particle has a hidden super partner. For every quark there is a squark, for every electron a selectron. For every force-carrying particle like the photon, a photino. In a perfectly supersymmetric universe, these partners would be identical in mass to their counterparts, creating a beautiful, doubled symmetry in the laws of physics. This symmetry does more than just add new particles to the list. It provides a powerful stabilizing effect on the very fabric of reality. The quantum jitters of ordinary particles tend to drive the energy of the vacuum, the cosmological constant, to impossibly high values. But in supersymmetry, the contributions from particles and their superpartners are perfectly opposite. They cancel each other out like two perfectly matched waves that meet and flatten into calm water. This cancellation tames the wild quantum fluctuations, leaving behind a vacuum landscape that is far more stable and manageable. It creates a vast, flat plane in the energy terrain, a plateau where the universe can exist without immediately tearing itself apart. The theory suggests that in its earliest, hottest moments, our cosmos did inhabit this perfectly symmetrical state. It was a realm of ultimate simplicity where matter and force were mirrored, and the vacuum energy was held in a delicate, balanced suspension. But we do not live in that universe today. We see electrons but no selectrons. We see photons but no photinos. Supersymmetry, if it exists, is broken. The diverse particles and forces we observe, with their wildly different masses and properties, are the shattered pieces of that primordial symmetry. This is where the story of quantum tunneling reaches a pivotal moment. The transition from that flat, supersymmetric plateau to our current, complex reality may not have been a gentle slide. It could have been a sudden, catastrophic leap. Imagine that flat plane is not the lowest energy state available. Beneath it, hidden by a quantum barrier, lies a much deeper, more complex valley, our current vacuum with its broken symmetry and rich particle zoo. The early universe, cooling from its fiery birth, found itself trapped on that high plateau. It was metastable like a ball balanced on the rim of a bowl. Classically, it might have stayed there, but through a quantum tunneling event, it made the jump. The entire cosmos, or a region of it, vanished from the supersymmetric state and reappeared in the lower energy, broken symmetry valley. This tunnel would have been monumental. It would have released an enormous amount of potential energy that could have directly fueled the inflationary expansion that shaped the cosmos. In one single quantum event, the universe could have accomplished two universe-defining tasks. It broke the perfect symmetry of its youth, giving birth to the diverse world we know, and it unleashed the driving force that set the stage for galaxies, stars, and planets to form. Our reality, in all its beautiful, asymmetric complexity, may be the direct result of a single probabilistic leap from a state of perfect, silent order. Supersymmetry's broken perfection gave us a rich, diverse cosmos, but it leaves the stage set on a single, three-dimensional sheet. What if our entire universe is just one page in a multidimensional book? This 11th theory, the ekpyrotic or cyclic model, proposes exactly that. It reimagines our cosmos not as an isolated bubble, but as a three-dimensional membrane, or brane for short, floating within a hidden, higher-dimensional expanse. In this brane cosmology, the familiar particles and forces we know are trapped on our brain like ink on a page, unable to escape into the full bulk of higher-dimensional space. But gravity can leak through, a faint whisper of the greater reality beyond our sheet. The story begins with not one, but two of these cosmic sheets, parallel to each other in the higher dimensional void. For most of eternity, they float in serene, empty darkness, slowly drifting on a gentle attraction. Then, drawn together by the subtle pull of gravity across the bulk, they begin to approach. This is not a violent, head-on crash, but a graceful, drawn-out convergence. As the branes draw nearer, the space between them compresses. Energy builds in that interstitial gap, stretching and warping the fabric of the branes themselves. From our perspective, trapped on one of these sheets, this approach would not look like an impending collision. Instead, it would manifest as a period of slow, crushing contraction. The universe would appear to be getting denser, hotter, and smaller, as if rewinding the expansion we see today. This is the ekpyrotic phase, a long, slow squeeze that smooths out the cosmos, ironing out any wrinkles or irregularities, preparing a perfectly flat, uniform slate. Then the brains meet. They do not pass through each other, but collide and rebound like two sheets of rubber snapping apart. In that moment of contact, the pent-up energy between them is released in a cataclysmic flash. That flash, from our trapped perspective on the brain, is the Big Bang. All the matter, radiation, and heat of our universe is born from the kinetic energy of that collision. The rebounding brains then fly apart, initiating the expansion we now observe, an expansion that will eventually slow, halt, and reverse as gravity pulls them back together for another cycle, trillions of years in the future. But where does quantum tunneling fit into this grand cyclic dance? The approach of the brains through the higher dimensional space may not be a simple classical fall. They could be separated by a potential barrier, a kind of hill in the bulk geometry that they lack the classical energy to roll over. Their eventual collision, then, would be the result of a quantum tunnel, a probabilistic leap that brought them into contact. Even more profoundly, the brains themselves and the higher dimensional bulk they float within may not be eternal. They too could have quantum tunneled into existence from a state of nothing, a higher dimensional instanton giving birth to the entire arena in which this endless cycle of creation and destruction plays out. In this view, our Big Bang was not a beginning from nothing, but a turn in an eternal, rhythmic process, a cosmic heartbeat made possible by a quantum leap in the dark. The smooth, rhythmic collisions of cosmic brains depend on a steady, forward-flowing time. But what if time is not a fundamental river, but a structure that had to be built? Theory 12 ventures into the deepest philosophical waters, proposing that time itself, the very stage on which all cosmic events play out, is a product of quantum tunneling. In this radical view, the Big Bang was not just the birth of space and matter, but the moment time crystallized from a formless quantum possibility into the one-way arrow we experience. To grasp this, we must first let go of our most basic assumption that time has always flowed. In the extreme conditions of the universe's origin, the distinction between time and space may have dissolved into a quantum foam, a seething probabilistic soup where every possible configuration of reality flickered in and out of existence. In this primordial state, before and after had no meaning, time was not a flowing river but a jumbled heap of all potential sequences, a variable in a state of quantum superposition. It existed in every possible order simultaneously, with no preferred direction, no cause, and no effect. It was pure potential without history. The transition from this timeless quantum foam to our orderly, sequential universe then becomes the ultimate quantum leap. The universe did not tunnel through a barrier in space, but through a barrier in possibility, from a state where time is undefined to one where it is definite. This is the tunneling of time itself, the instanton, that mathematical blueprint for the transition, would not describe a path through space, but a path from timelessness to temporality. Think of it like the moment a random quantum fluctuation in a supercooled liquid triggers the formation of a perfect ice crystal. Before that moment, the water molecules are jostling in every direction with no overall structure. After the nucleation event, a rigid, ordered lattice snaps into place, defining clear positions and relationships. The tunneling event at the beginning of everything may have been similar, a nucleation of time from chaos. It selected one specific direction from the infinite superposition, collapsing the quantum possibilities of when into a single, irreversible sequence. This event did not happen in time, it created time. The first moment of classical time was the far side of that quantum tunnel. The implications of this are dizzying. It suggests causality. The rule that cause must precede effect is not a fundamental law of the cosmos, but an emergent property. It arose when time tunneled into existence, bringing with it the unbreakable chain of sequence that governs our reality. The arrow of time, always pointing from past to future, may not be an intrinsic feature of the universe, but the scar of that primordial transition, the direction in which the quantum dice fell when reality made its leap from potential to actual. We perceive time as flowing because our entire conscious experience is embedded in the classical universe that resulted from that one cosmic-scale quantum decision. Every sunrise, every heartbeat, every moment of memory is a consequence of that foundational tunnel, a ripple in a stream that began flowing only when the universe chose its direction from timelessness. The crystallization of time from a quantum possibility redefines the very stage of reality, but what about the actors upon it? The 13th theory proposes that the universe's entire content, every galaxy, star, and atom, might be a grand illusion projected from a lower dimensional blueprint. This is the holographic principle, and its connection to our origin story suggests the Big Bang was not an explosion of matter, but the projection of cosmic information. The principle emerges from the physics of black holes, where a profound puzzle was solved. The entropy or information content of a black hole was found not to be proportional to its volume, as one might expect, but to the area of its event horizon. This hinted that all the information describing everything that fell into the black hole was not lost inside its vast interior, but was somehow encoded pixel by pixel on its two-dimensional surface. Extrapolating this staggering idea to the cosmos, some physicists propose our entire three-dimensional universe, with its rich depth and structure, could be a holographic projection from information stored on a distant, two-dimensional boundary that encloses all of space. We are not living inside the reality, we are living inside a three-dimensional movie projected from a two-dimensional cosmic film. This transforms our understanding of the universe's quantum birth. The initial tunneling event may not have created a three-dimensional volume filled with energy. Instead, it could have been a quantum leap in information state on a lower dimensional surface. Picture a vast featureless screen, a boundary of pure potential. On this screen, quantum bits of information, or qubits, exist in a seething, probabilistic superposition. Then a tunneling event occurs. A specific, stable pattern of information crystallizes from the quantum noise on that two-dimensional boundary. This pattern is not a picture of a universe, it is the universe encoded in its most fundamental data. The act of tunneling this information into a classical state then triggers a projection, inflating that data into the full, three-dimensional spatial reality we perceive. The expansion of space, the formation of particles, the very laws of physics themselves, would all be emergent phenomena, shadows cast by the dynamic information processing happening on that distant cosmic screen. In this view, the birth of our cosmos was the ultimate quantum computation. The universe did not tunnel from nothing into something. It tunneled from a quantum probability wave into a definite state of information on a lower dimensional surface, and that information processing event is what we experience as reality. We are not just made of stardust, we are made of cosmic code, and the first line of that code was written in a single, probabilistic quantum leap. The holographic universe paints reality as a cosmic projection, yet it leaves a haunting question about the projector itself. Could the act of observation be the ultimate power switch? This 14th theory ventures into the most speculative and profound territory of all, proposing that the universe required a witness to be born. It ties the cosmic quantum tunnel directly to the infamous measurement problem in quantum mechanics. In the quantum realm, particles exist not as definite objects, but as clouds of probability called wave functions. An electron is not here or there, it is everywhere it could possibly be, all at once, in a blurred state of superposition. This strange condition persists until the moment it is measured or observed. Then, in an instant, the wave function collapses, all those ghostly possibilities vanish, and the electron appears in one specific location. its probability cloud crystallizing into a concrete fact. The universe at its inception may have been in an analogous state. It was not a definite, expanding cosmos, but a superposition of all possible universes, a wave function of cosmic potential hovering in the realm of quantum nothingness. It was everything and nothing, everywhere and nowhere, waiting, according to this highly speculative idea that waiting ended with a measurement. A primordial act of observation collapsed the universal wave function. But who or what could possibly have been the observer before anything existed? The theory offers mind-bending possibilities. Perhaps the observer was not a being, but a self-referential loop within the quantum laws themselves. The universe's own potential to contain observers in the future could have reached back and triggered its own birth, a bootstrap of consciousness. Or, in a many-worlds interpretation, every possible universe did come into existence, but our specific branch, the one we experience, was selected by the first quantum observation within it, a tunnel from possibility to actuality initiated by its own internal logic. This leads to the staggering philosophical implication of a participatory universe, a cosmos that did not simply happen, but was realized. It suggests that existence is not a passive stage, but a dynamic interaction between reality and the act of witnessing it. We are not just accidental inhabitants of a random cosmos. Our very capacity to observe, to measure, to be conscious, might be woven into the foundational fabric of reality, a necessary ingredient that allowed the universe to tunnel from pure potential into the majestic, tangible reality we now explore. The universe's birth may not have been a cold, probabilistic leap from nothing, but a hot, seething event driven by the most fundamental force in nature, the relentless drive toward disorder. This 15th theory, the thermal tunneling scenario, rewrites the origin story by bringing thermodynamics into the quantum realm. It begins with a cosmos before the cosmos, not as empty nothingness, but as a roiling, infinite sea in a state of perfect thermal equilibrium. Think of a pot of water on a rolling boil. The energy is distributed evenly, with bubbles forming and popping chaotically at all scales. In this primordial quantum gravitational soup, every possible configuration of energy and space-time flickered in and out of existence, a turbulent, timeless chaos where the concepts of before and after held no meaning. This was a state of maximum entropy, a formless, energetic fog where nothing ever happened because everything was constantly happening all at once. It was the ultimate cosmic dead end, a boring, featureless eternity. For anything interesting to emerge from this soup, a miracle was needed. Not a miracle of design, but a statistical fluke. In any system governed by thermodynamics, even in perfect equilibrium, random fluctuations occur. Most are tiny and insignificant, a momentary clustering of energy here or there that instantly dissipates back into the background noise. But the laws of statistics allow for a possibility, however remote, of a truly gigantic fluctuation. A massive, coherent surge of energy concentrated in one region of the soup, like a single, enormous bubble forming in the boiling pot. This rare, colossal thermal fluctuation would be the seed of everything. This bubble of concentrated energy would not be stable in the old, high-entropy state. It would be a region desperate to transition to a more stable, lower-energy configuration, a new phase of reality. But to get there, it would have to cross a barrier. The energy landscape between the old, chaotic phase and the new, orderly one would present a mountain it could not classically climb. Here is where the quantum magic happens, this massive thermal fluctuation, riding a wave of sheer statistical luck, could provide just enough concentrated energy to make a quantum tunnel through that barrier not only possible but probable. It would be a thermal assist for a quantum leap. The bubble, fueled by this rare statistical event, would vanish from the old, boiling soup and reappear as a region of new vacuum, a pocket of lower energy and higher order. This transition would break the symmetry of the featureless soup, defining new laws and particles within that bubble, and crucially, the energy difference between the old state and the new state would be titanic. When the bubble tunneled into existence, all that excess energy would be released in a ferocious outward push. This release would be the trigger for inflation, causing that tiny, tunneled bubble to undergo a violent, exponential expansion, rapidly cooling and smoothing into the embryonic universe we recognize. In this thermal tunneling scenario, the Big Bang was not a beginning from nothing, but a cosmic phase change, like the moment steam condenses into a droplet of water. Our entire reality is that droplet born from a rare shiver in an infinite hot sea, a statistical anomaly that tunneled into permanence. That hot, seething statistical fluctuation gave birth to our cosmos, but it left a deeper question unanswered. Why do we find ourselves in a universe with these specific rules, with electrons this heavy and gravity this weak? The answer may lie in an invisible, unimaginably vast library of possibilities, and the single, random shelf our universe happened to land on. This is the profound implication of Theory 16, the string theory landscape, and the quantum tunneling event that selected our cosmic address. String theory, our most ambitious attempt to describe all of reality, suggests the fundamental ingredients of the cosmos are not tiny dots but vibrating loops of energy. To make the mathematics of these vibrating strings consistent, the theory requires extra dimensions of space, not just the three we experience, but these extra dimensions are not stretched out like our familiar ones. They are curled up, twisted into fantastically complex tiny shapes known as Calabi-Yau manifolds. The way these shapes are folded, the precise pattern of their twists and holes, is not arbitrary. It determines everything about the physics in the larger, four-dimensional universe they inhabit. The specific fold dictates the number and type of particles that exist, the strengths of the fundamental forces, the mass of the electron, the value of the cosmological constant, every single constant and law we take for granted. And here is the staggering part. There is not just one way to fold these extra dimensions. The number of stable, possible configurations is astronomically large, estimated to be around 10 to the power of 500. That is a 1 followed by 500 zeros, a number so vast it exceeds all the atoms in our observable universe. This is the string theory landscape, a cosmic terrain of possible realities so immense it defies human comprehension. Each stable configuration, each specific fold of the extra dimensions, corresponds to a different valley in this landscape, a different vacuum state with its own unique, self-consistent set of physical laws. Our universe, with its particular particles and forces, is just one valley. There are valleys where gravity is 1 billion times stronger, snuffing out stars instantly. Valleys where electromagnetism is too weak to hold atoms together. Valleys where nuclear forces cannot forge carbon, making life impossible. Valleys of every conceivable permutation, a near infinity of dead, sterile, or wildly exotic cosmic recipes. So how did we end up in this one remarkably life-friendly valley? The mechanism is the same one we have been following all along: quantum tunneling. In the earliest moments, as the universe emerged from the quantum foam or a higher dimensional collision, it was not predestined for our specific vacuum. The nascent cosmos, represented by the values of its fields, including the geometry of those extra dimensions, was exploring this vast landscape. It could have rolled, fluctuated, or tunneled into any one of those 10 to the 500 possibilities. The journey from the initial high-energy state to a stable, expanding universe likely involved a cascade of quantum tunnels, a random walk down the energy hills of the landscape. Our universe's specific set of constants was not chosen. It was stumbled upon. Through a probabilistic quantum leap, the fields describing the cosmos tunneled from a higher energy configuration into our particular low-energy valley, locking in the folds of the Calabi-Yau manifold that define our reality. In that instant, the electron received its mass, the forces their relative strengths, and dark energy its curiously tiny value. This transforms the mystery of our universe's apparent fine-tuning from a puzzle of design into a matter of statistics. In a landscape of infinite possibilities, every possible universe exists somewhere. We do not observe a fine-tuned cosmos because it was made for us. We observe it because we could only arise in a cosmos that tunneled into a valley capable of producing stars, planets, and curious minds. Our existence is the aftermath of a single, random quantum selection from a near-infinite menu of realities. The landscape of string theory offers an infinity of possible homes, but what if our cosmic home was built from the most absolute foundation imaginable, a state of literal nothingness with not even space to call its own? This 17th theory, the null boundary proposal by physicist J. Richard Gott, takes the idea of creation from nothing to its logical and mathematical extreme. It suggests our universe did not tunnel from a quantum vacuum or a pre-existing bulk. It tunneled from a state of zero volume where the very concepts of here and now did not exist. This is not a void waiting to be filled, but true nothingness, a complete absence of spacetime itself. The proposal provides a startlingly concrete, if complex, mathematical picture for how this could happen. In quantum mechanics, the uncertainty principle allows for temporary violations of energy conservation. Particles can pop into existence from empty space, borrowing energy for a fleeting moment before vanishing again. Gott's idea applies this principle to the entire geometry of the cosmos. He proposes that a tiny, closed universe could spontaneously nucleate from nothing, its entire history appearing all at once in a single quantum event. The key to visualizing this lies in the boundary of this newborn universe. In most models, a universe has a space-like boundary, a kind of edge in space at the beginning of time. But in the null boundary proposal, the universe is bounded by a light-like surface, also called a null surface. This is a surface formed by light rays themselves. Think of a flash of light at a single point. The expanding sphere of that light, traveling outward at light speed, defines a null boundary. It is not a wall in space, it is the leading edge of causality, the very first signal that anything exists. Gott's model suggests the universe tunneled into being as a microscopic, self-contained spacetime region bounded by just such a light-like shell. From the outside, if there could be an outside, this would appear as a momentary flicker of light, a bubble of reality with zero initial size. From the inside, this null boundary is the beginning of everything. In that instant of tunneling, space is created within the bubble, and time begins to flow forward from that boundary. The null surface is both the moment of creation and the first tick of the cosmic clock. The mathematics shows that such a universe, once created, would naturally begin to expand under its own internal energy, driven by a positive cosmological constant or an inflattened field. So the sequence is breathtaking in its simplicity. From absolute nothingness, a quantum fluctuation generates a closed universe of zero size bounded by a shell of light. That tunneled bubble immediately inflates, its null boundary racing outward as space itself stretches and time unfolds within it. In one single quantum leap, the proposal creates space, time, matter, and the arrow of causality simultaneously. It offers a stark and elegant answer to the ancient question of how something can come from nothing. The universe did not appear in a pre-existing void. It brought the void into existence with it, defining its own arena of reality in the very act of being born. The universe's null boundary birth creates a clean slate, but it leaves a profound asymmetry unexplained. Why does time only move forward? The 18th theory suggests the answer is etched into the very moment of creation, proposing that the quantum tunnel which birthed our cosmos also fired the starting gun for time's irreversible arrow. Our everyday experience is ruled by a simple, relentless truth. Eggs scramble but never unscramble. Ice cubes melt in your drink but never spontaneously reform. Memories are of the past, never the future. This is the arrow of time, the one-way direction from order to disorder described by the second law of thermodynamics, which states that entropy or disorder always increases in a closed system. Yet this law presents a monumental puzzle. If disorder always increases, then the universe must have started in a state of incredibly low entropy, a condition of exquisite, improbable order. Why was the cosmic deck of cards so perfectly stacked at the beginning? The answer may lie in the geometry of the quantum tunnel itself. When the universe transitioned from nothing or from a prior state, it did not take just any path. The instanton, that mathematical blueprint for the tunnel, describes the most probable route. This pathway is not symmetrical. It has a distinct shape, a specific contour that favors one direction over the other. Think of the tunnel not as a round, smooth pipe, but as a chute with a gentle slope on one end and a steep drop on the other. The universe emerged on the steep side, the low entropy side. The very act of tunneling selected this asymmetric configuration, setting the initial conditions with the entropy wound incredibly tight, like a cosmic spring. This low entropy beginning is not an accident, it is a signature of the tunnel. It is the reason the Big Bang was so uniform and smooth, a state of extraordinary order compared to the chaotic, high-entropy possibilities that could have emerged. From that precise starting point, the spring began to uncoil. Gravity pulled matter into galaxies and stars, nuclear furnaces ignited, and complexity grew, all while the total entropy of the universe marched steadily upward, driving the arrow of time forward. In this view, the flow of time we feel every second of our lives is not a fundamental property of empty space. It is a direct inheritance, a consequence of the specific, asymmetric quantum leap our universe took at its birth. The reason we remember the past and not the future is because we are living downstream from that single, probabilistic event, riding the wave of increasing disorder it set into motion on the very first day. The arrow of time gave our universe its direction, but what provided its blueprint for structure? The 19th theory proposes a hidden architect, one that wove connections into the fabric of reality at the very moment of creation. This is the profound role of quantum entanglement in our origin story. While tunneling explains how the universe emerged, entanglement may explain how it became a coherent, interconnected whole. In the quantum world, entanglement is a phenomenon so strange it baffled even Einstein, who called it spooky action at a distance. It occurs when two particles become linked, their fates intertwined no matter how far apart they are separated. Measure the spin of one particle, and the spin of its partner instantly becomes known, as if information has traveled faster than light. This is not a signal, but a deeper correlation written into the foundation of reality. The theory suggests that the primordial quantum tunneling event did more than just create particles and expand space. It also created the very first quantum correlations. As the universe tunneled from its initial state, it did not emerge as a collection of independent, disconnected points. It was born entangled. A vast, invisible web of quantum connections was spun in that first instant, linking every region of the nascent cosmos to every other. This initial entanglement was not a minor detail. It was the cosmic canvas upon which everything else would be painted. Think of the early universe as a blank sheet of paper being prepared for a watercolor painting. The quantum tunneling event provided the water, the raw potential of existence. But the entanglement web provided the sizing, the subtle, invisible treatment that controls how the paint will spread and where the pigment will gather. Without it, the paint would just blot and run chaotically. With it, beautiful, coherent structures can form. In the cosmic context, this means the subtle variations in density that we see in the cosmic microwave background, the faint fingerprints of the infant universe, were not random noise. They were the direct imprint of that primordial entanglement. Regions of space that were quantum entangled at birth exhibited correlated properties, tiny differences in temperature and density that were in sync across vast distances. These correlated wrinkles, frozen into the fabric of space-time during inflation, became the gravitational seeds for everything to come. Where the entanglement was strongest, where those quantum correlations created a slightly denser patch, gravity got an early start. Over billions of years, those patches drew in more and more matter, eventually collapsing into the vast cosmic web of galaxies, clusters, and superclusters we observe today. The galaxies we see are not scattered randomly. They trace out filaments and walls, a grand architecture that mirrors, on an unimaginable scale, the web of quantum connections forged in the universe's first fleeting moment. In this view, the large-scale structure of the cosmos, the greatest pattern we can observe, is not a product of chance alone. It is the ghostly, amplified echo of a quantum handshake that happened when reality itself was born, a silent conversation between distant parts of the universe that began before time had fully taken hold. That web of quantum entanglement hints at a deeper truth, that space itself may be woven from connections. But what if space is not a fundamental stage, but a pattern that crystallized from chaos? This 20th theory takes us to the frontier of physics, to a concept known as quantum gravity. In this radical picture, the smooth, three-dimensional expanse we move through is not primary. It is an illusion, a collective behavior that emerges from something far more basic. Imagine the deepest foundation of reality not as a continuous fabric, but as a vast, shifting network. A cosmic web of unimaginably tiny nodes, like dots on an infinite graph, connected by links that can be on or off, strong or weak. In its raw, primordial state, this network is a seething quantum frenzy. Every node is connected to every other node in a chaotic, all-to-all tangle. This is a pre-geometric phase, a state before space as we know it exists. There is no distance, no dimension, no here or there, only a boiling pot of pure connection. It is a formless, high-energy chaos where the very concept of location is meaningless. The birth of our universe, according to this theory, was not an explosion in space, but a freezing of this network. It was a quantum phase transition, a tunnel from chaos to order. Through a probabilistic leap, the dynamic network found a path to a new, stable configuration. The countless, frantic connections of the chaotic state suddenly simplified. The network tunneled into a regular, low-energy pattern where each node is connected only to a handful of its nearest neighbors. And this specific, orderly pattern of connections is what we perceive as three-dimensional space. The reason we experience up and down, left and right, forward and backward is because that is the geometry of the network's connections in its cooled, crystalline state. Distance is not a fundamental measure. It is derived from how many links you must traverse to get from one node to another. In that moment of tunneling, the network did not just become orderly, it became dynamic. The new, stable configuration possessed an inherent energy that caused it to expand. As the network evolved, the number of nodes participating in the pattern increased and the links between them stretched. From our emergent perspective, trapped within the pattern, this stretching of the graph is what we experience as the expansion of the universe. The Big Bang, then, was the moment the quantum graph found its groove. It was the instant the cosmic network tunneled from a buzzing, formless hive of unlimited connections into a quiet, regular lattice, and that lattice's subsequent growth is the story of our cosmos. We are not living in a container called space. We are living inside a pattern, a cosmic computation that found its stable state through one quantum leap. The pattern of a quantum graph offers a profound possibility that our reality is a computation. But what if that is not just a metaphor? What if it is the literal truth? This 21st theory dares to ask if our universe is a simulation, and reimagines the Big Bang not as a cosmic explosion, but as a system booting up. The simulation hypothesis, popularized in philosophy and science fiction, suggests our entire reality could be an artificial construct, a detailed model running on a computer of unimaginable power in some base level of existence. While this idea often feels like pure speculation, physics provides a startlingly concrete way to frame it through the lens of quantum information. In this view, the cosmos is not made of atoms and forces in the traditional sense. It is made of quantum bits or qubits, the fundamental units of quantum information. Every particle, every field fluctuation, every ripple of space-time is a state within a vast cosmic quantum computer. The moment of creation, then, was not a fiery bang, but a quantum initialization sequence. Picture the ultimate computer, cold and silent in a state of potential. Its quantum registers, the memory units that will hold the data of a universe, are in a state of superposition, representing every possible universe that could be simulated. To begin a specific simulation, you must collapse that potential into a definite starting state. You need a controlled, precise quantum event to write the first line of code. This is where our story of tunneling returns with a new purpose. The Big Bang in this framework was that controlled tunneling event. It was the moment the simulation's master program executed a quantum operation, causing the cosmic quantum registers to tunnel from a state of pure, undifferentiated potential into a specific, programmed initial condition. This tunnel set the seed values for every physical constant, the strength of gravity, the mass of the electron, the value of pi. It wrote the laws of physics into the very fabric of the simulation as immutable parameters. The rapid inflationary expansion that followed would be the simulation's rendering engine kicking into high gear, generating the vast, detailed landscape of spacetime from that initial seed data. The cosmic microwave background radiation we detect could be seen as the thermal noise of the processor, the faint hum of the simulation's hardware imprinted on the first frame. This perspective transforms the mystery of our universe's fine-tuned laws from a question of cosmic luck or divine design into one of engineering. Why is the cosmological constant so small? Because that was an efficient value for the simulation's stability. Why do we have 3 spatial dimensions? Because that was the chosen architecture for the simulation's rendering. The quantum tunneling that birthed our reality was not a random fluctuation, but a deliberate, programmed instruction in a higher dimensional source code, the first tick of a cosmic clock that began counting the cycles of a grand, artificial reality. A simulated reality presents a universe of perfect, programmed parameters, but our own cosmos reveals a puzzling and profound imbalance in its very foundations. This is the hierarchy problem, a mystery that cuts to the heart of why our universe looks the way it does, and the 22nd theory suggests its resolution was written into the moment of our quantum birth. The problem is simple to state but baffling to solve. The fundamental forces of nature are wildly mismatched in strength. The strong nuclear force that binds atomic nuclei is a titan, electromagnetism is a powerful giant, and the weak nuclear force is still formidable. But gravity, the force that sculpts galaxies and holds planets in orbit, is almost impossibly feeble. It is weaker than the other forces by a factor of 1,000 trillion. That is a 1 with 39 zeros after it. To put this in perspective, the difference in strength between gravity and electromagnetism is like comparing the weight of a single bacterium to the mass of our entire planet. This gap is not just a curiosity, it is a crisis for physics. In our best theories, the energy scale of the quantum vacuum should naturally pull all forces to a similar, incredibly high strength. Something must be actively, precisely fine-tuned to keep gravity so absurdly weak while the other forces remain strong. The proposed solution lies in the specific pathway our universe took during its primordial quantum tunnel. Recall the inflattened field, the entity that powered cosmic inflation, and its energy landscape of hills and valleys. The tunneling event that birthed our cosmos was not a random jump into any low point. It was a precise journey through that landscape, a path dictated by the mathematics of the instanton. This pathway did not just determine that a universe would form, it dynamically set the energy scales for everything within it. As the inflattened field tunneled from its false vacuum, the shape of the barrier it traversed and the contours of the valley it landed in were intrinsically linked to the final resting values of all the other quantum fields. The depth of the valley, the steepness of the slopes, these geometric features in the abstract space of possibilities translated directly into the masses of particles and the relative strengths of forces in our newborn reality. In this view, gravity is not inherently weak. Its apparent feebleness is an emergent property, a consequence of the specific cosmic address we tunneled into. The tunneling event locked the Higgs field, which gives particles mass, into a specific value, while simultaneously setting the scale for the quantum fluctuations of spacetime itself, which we feel as gravity. The vast hierarchy we observe is not a bug, it is a feature of that one particular quantum path. This leads to an anthropic explanation, a reasoning based on our own existence. In the string theory landscape with its 10 to the 500 possible universes, only those that tunneled into valleys producing this specific, extreme hierarchy could possibly support life. If gravity were even a little stronger, stars would burn through their fuel in a cosmic blink, never allowing planets to form or life to evolve. If the nuclear forces were weaker, atoms could never fuse into the carbon that builds our bodies. Our presence here, asking this question, is therefore a direct consequence of that initial tunnel. We do not observe a universe with a puzzling hierarchy because we are lucky. We observe it because we are the products of the one quantum pathway out of an unimaginable number that led to a cosmos capable of asking why. The staggering weakness of gravity, then, is not a problem to be solved, but a signature of our cosmic origin story, a permanent reminder of the precise leap our reality took from nothing to everything. That staggering hierarchy of forces is a permanent signature of our universe's specific quantum pathway, yet it raises a deeper question about the ultimate fate of everything it has built. What happens when the last star dies, the last black hole evaporates, and the cosmos drifts into a cold, dark eternity? The answer may not be an end, but a transformation so profound it requires a tunnel back to the beginning. This is the 23rd theory, a vision that ties our quantum origin to the far future through Roger Penrose's conformal cyclic cosmology. Penrose proposes that our universe is not the first, nor will it be the last in an endless sequence he calls eons. Each eon begins with its own hot, dense Big Bang and expands over trillions of years into a featureless, lifeless void. But in this model, that void is not a dead end. It is a bridge. As an eon approaches its final state, all matter eventually decays. Protons dissolve, black holes evaporate via Hawking radiation, and even the most stable particles break down. What remains is a universe of pure, massless radiation, photons and gravitons racing through an ever-expanding, utterly empty space. In this state, something remarkable happens to the geometry of the cosmos. Because there is no mass to define a scale, the universe becomes effectively scale-less or conformally invariant. A single photon traveling across this infinite emptiness experiences no meaningful change in scale from one moment to the next. The remote, infinitely stretched future of one eon becomes geometrically identical to the hot, dense, ultra-compressed beginning of another. They are two sides of the same conformal coin. But how does the universe jump from the cold, silent end of one eon to the fiery birth of the next? The theory suggests a quantum tunnel stitches them together. The transition is not a classical, continuous process. It is a leap. At the conformal boundary where one eon meets the next, the universe's state must undergo a radical reset. The cosmological constant, the energy of empty space that drives acceleration, must drop to zero. The slate must be wiped clean for a new set of physical constants to emerge. This reset could be achieved through a grand cosmological scale quantum tunneling event. Picture the final state of an eon as a wide, flat valley of pure radiation. The beginning of the next eon is a different valley entirely, one of ultra-high density and temperature. Between them lies a barrier, a region of potential energy where the laws of physics as we know them do not apply. The information and structure of the old universe, encoded in its gravitational waves and radiation, does not have the energy to classically cross this barrier. Yet, through a probabilistic quantum tunnel, it can. The entire conformal structure of the old eon could vanish from its final state and reappear as the initial quantum fluctuation for the next. This tunnel would not preserve matter or galaxies, those are long gone. It would preserve only scale-less information, the conformal shape of reality itself, which then gets reinterpreted as the seeds for new structure in the reborn cosmos. In this breathtaking cyclic vision, the Big Bang is not a beginning from nothing, but a quantum resurrection. Our universe tunneled into existence from the infinitely diluted remains of its predecessor. And in the distant, distant future, when our eon has faded to a silent sea of light, it will itself become the nothing from which a new cosmos will quantum leap into being, in an endless, elegant cycle of dissolution and rebirth. The smooth, endless cycles of eons are a cosmic symphony, but the universe we observe is not perfectly uniform. It is textured, structured, and filled with intricate patterns. The origins of that texture might be found in cosmic scars, frozen relics of the universe's most violent growing pains. These are topological defects, and their birth may have been a quantum shout in the early cosmic silence. As the universe cooled from its unimaginably hot beginning, it underwent a series of dramatic phase transitions akin to water freezing into ice. When water freezes, the ice crystals form in different orientations. Where these differently oriented crystals meet, a flaw appears in the structure, a boundary or crack. In the early cosmos, the thing that was crystallizing was not water, but the very fields that govern reality. As the universe expanded and cooled, the Higgs field and other fundamental fields settled into their stable, low-energy states, but they did not settle the same way everywhere. In some regions, the field might have chosen one orientation. In another region, far away and out of contact due to the universe's rapid expansion, it chose a different, equally valid orientation. When these cosmic domains of differently oriented fields eventually met as the universe grew, they could not simply merge seamlessly. The mismatch created a persistent kink, a defect frozen into the fabric of spacetime itself. These defects come in different forms depending on the geometry of the field. A cosmic string is a one-dimensional defect, an infinitely long, unimaginably thin filament of concentrated energy. A crack in spacetime so dense that a single inch of it could weigh as much as a mountain range. A domain wall is a two-dimensional sheet, a vast, impermeable membrane separating regions of the universe with different physical properties, and textures are more subtle, not like configurations that can unwind, releasing energy. But here is the profound twist. The formation of these defects might not have been a simple, classical snapping into place. The transition from a symmetric, high-energy state to a broken symmetry, low-energy state often requires crossing a potential barrier. In many regions, the field could have rolled slowly down the energy hill, but in others, it may have taken a shortcut. Through quantum tunneling, a patch of the primordial field could have vanished from the symmetric state and instantly reappeared in a specific broken symmetry state all at once. This sudden, probabilistic leap would have created a region of space with a definitive field orientation, immediately surrounded by regions still in the old state. The boundary of this tunneled bubble would be a sharp defect line, a cosmic string or the edge of a domain wall, born not from a slow freeze but from an instantaneous quantum decision. These tunneled defects were not just cosmic curiosities, they could have been the architects of our reality. A network of cosmic strings woven from quantum tunnels would have crisscrossed the infant universe. Their immense gravity could have acted as the first seeds for matter to cluster around, providing a scaffolding for the cosmic web long before the subtle quantum fluctuations from inflation had a chance to grow. In some models, a single, specific type of defect tunneled into existence could have itself triggered a new round of inflation, its core energy driving a brief, violent expansion that smoothed and shaped its local region of the cosmos. So when we map the large-scale structure of galaxies today, we may be looking at the fossilized imprint of quantum tunnels that happened in the first fraction of a second, cracks in the cosmic egg that guided the formation of everything within it. Cosmic strings and domain walls are scars from the universe's violent youth, but they also point to a terrifying possibility. If quantum fluctuations can create such immense structures, what else might they create given enough time? The answer leads us to one of the most unsettling ideas in all of cosmology, the Boltzmann brane paradox. This thought experiment, born from statistical mechanics, suggests that in a vast, eternal, and random cosmos, the most likely conscious entity is not a person in a universe, but a single, disembodied brain. Imagine an infinite, chaotic void where particles jostle at random for all eternity. Given enough time, every possible configuration of matter will occur by sheer accident. It is statistically far more probable for a random fluctuation to assemble a single, fully formed, conscious brain with false memories of a past and a universe than it is for a fluctuation to create an entire, ordered cosmos spanning billions of light years. The odds of popping a perfectly assembled watch out of a tornado in a junkyard are astronomically low, but the odds of popping out a single, working gear are far higher. In an eternal, high-entropy sea, you would expect countless of these isolated, self-aware moments to flicker into existence, each convinced it lives in a real, structured world, only to dissolve back into chaos an instant later. This presents a devastating philosophical problem. How can we trust that our memories, our science, and this vast universe are real, and not just the fleeting, accidental hallucination of a Boltzmann brain floating in the void? The answer may lie in the specific nature of our origin story, in that initial quantum tunnel. While both a full universe and a Boltzmann brain are incredibly improbable quantum events, they are not equally improbable. Tunneling directly from chaos to a single, complex, conscious object like a brain requires an immense and precise leap. It must assemble trillions of precisely connected neurons, create coherent memories, and sustain that configuration long enough for a subjective experience, all in one random jump. The probability is vanishingly small, but tunneling from nothing to a low-entropy, inflating universe is a different kind of event. It is not about assembling intricate parts, but about selecting a simple, smooth, and symmetric initial condition. The instanton pathway favors a state of maximum uniformity and minimal complexity, a blank slate with incredibly low entropy. This is a much broader, more natural target in the landscape of possibilities than the hyper-specific configuration of a functioning brain. Once that smooth universe exists, the laws of physics take over. Gravity and thermodynamics then work for billions of years to slowly, deterministically build complexity, forging galaxies, stars, planets, and eventually, conscious minds like ours through a long chain of cause and effect. We are not a random, one-step fluctuation. We are the end point of a reliable process that began with a simple quantum seed. Therefore, while both origins are statistically rare, the pathway that starts with a universe is exponentially more probable than one that creates a brain directly from the chaos. Our existence as embedded observers in a consistent, ancient cosmos is not the most likely hallucination. It is the most likely outcome of a very specific and powerful kind of quantum beginning. The Boltzmann brane paradox fades when we realize our universe did not win a lottery to assemble a watch from a tornado. It won a different, far more feasible lottery to create a single, perfect seed from which the watch could then grow, piece by logical piece, across the expanse of cosmic time. The terrifying specter of a Boltzmann brain forces us to confront the reliability of our cosmic memories, but it also points to a deeper truth about the structure of reality itself. If our universe grew from a simple, low-entropy seed, what is the fundamental substance of that seed? The answer may not be a smooth fabric, but a collection of discrete, irreducible moments. This brings us to Theory 26, a journey into causal set theory, where space-time is not continuous but granular, and the Big Bang was the quantum tunneling of the very first event. In this radical framework, the smooth, four-dimensional continuum of space-time we experience is an illusion, an approximation that emerges from something far more basic. The true foundation of reality is a causal set, a vast collection of elementary events like dots on a page, connected by a single, fundamental relation, the simple idea of before. One event either precedes another or it does not. There is no distance, no duration, no geometry in the traditional sense, only this vast, growing network of cause and effect. In the beginning, there was not a singularity of infinite density. There was nothing, not even an empty set. Then, through a quantum tunneling process, the first event sparked into being. This was not an explosion of energy, but the birth of causality itself. The universe tunneled from a state with no events, no relations, into a state containing one single foundational event. It was the genesis of before. From that solitary spark, creation unfolded not as an expansion of space, but as a growth of connections. New events did not appear in pre-existing locations. They quantum tunneled into existence, each one forging a causal link to at least one event that came before it. Picture a vast, dark void. A single point of light appears. Then, not far from it, another light winks on, connected to the first by an invisible thread of precedence. Then another and another, each new event tunneling into reality with a specific set of causal relationships to the events that already exist. This process is not smooth or continuous. It is a staccato burst of probabilistic births, a quantum cascade where each new event is a leap from possibility to actuality. Over an unimaginable number of these tunneling events, the network grows immense. Billions upon billions of these fundamental events, each connected in a specific web of before and after. And here is the miracle of emergence. When you have enough of these discrete events arranged with the right statistical properties, something remarkable happens. The pattern of their connections begins to approximate a smooth, continuous geometry. The order of events creates what we perceive as the flow of time. The density of connections in different parts of the network creates what we experience as the curvature of space and even the force of gravity. Our entire expanding universe, with its planets and stars, is the large-scale shadow cast by this ceaseless quantum tunneling of causal links. In this view, the Big Bang was not a location in space or a moment in time. It was the first causal relation. Everything that has happened since, every supernova, every falling leaf, every thought in your mind, is part of the ongoing cascade that began with that single, probabilistic leap from nothing to something that could cause something else. We are not living in a space-time that is stretching. We are living inside a story that is still being written, one quantum event at a time. The granular birth of causality paints a universe built from discrete events. But what is the nature of the arena in which this entire cosmic story unfolds? We have glimpsed baby universes budding from black holes, bubbles nucleating in a meta-cosmic sea, and cycles of eons reborn from silence. These are not separate possibilities. They are different views of the same staggering reality, a cosmos of cosmoses, all linked by the same fundamental mechanism. Our universe is not a solitary island. It is one branch in an infinite, bubbling tree, and the sap flowing through that tree is quantum tunneling. This is the vision of the multiverse as a dynamic tunneling network. Think of reality not as a static landscape, but as a living, ever-growing web. At each node of this web sits a universe, complete with its own space-time, particles, and laws. The connections between these nodes are not roads or bridges. They are quantum tunnels, probabilistic leaps where the fabric of one reality pinches off and blossoms into another. Each tunneling event is a cosmic branching point. A black hole singularity in a parent universe undergoes a quantum gravitational tunnel, and a new, infant universe buds from its heart. A false vacuum decay in one cosmic bubble triggers a tunnel, creating a new bubble with a different vacuum energy. Even the smooth conformal transition between eons can be seen as a tunnel across an eternal boundary. Every theory we have explored is a description of one type of connection in this vast network. In this network, our universe is not special or central. It is simply one node that tunneled into existence from a parent node, perhaps through a black hole collapse or a bubble nucleation trillions of years ago. And within our universe, every black hole that forms could, in turn, be spawning its own child universes, each with physical laws slightly varied from our own. The strength of gravity, the mass of the electron, the number of dimensions, these fundamental constants are not absolute truths written in stone. They are local bylaws determined by the specific quantum pathway our branch of the network took during its birth tunnel. A different tunnel, a different instanton, would have led to a different valley in the string theory landscape, a universe where stars might never form or where time flows backward. This transforms the multiverse from a philosophical idea into a physical prediction with a clear mechanism. The network is not just sitting there, it is actively growing, evolving, and branching with every possible quantum gravitational event. New nodes are constantly being added through tunnels, each one a fresh experiment in physics. Some branches are short-lived, tunneling almost immediately into a vacuum that collapses. Others, like ours, find a stable configuration that allows for billions of years of cosmic evolution and the rise of conscious observers. We find ourselves on a long, lush branch not because it was destined, but because only on such a branch could creatures like us arise to map the tree. The quantum tunnel that birthed our cosmos was not a one-time miracle. It is the most common form of cosmic reproduction in an eternally fertile reality. We are living in one leaf on a tree whose roots are lost in eternity and whose branches reach into futures we cannot fathom. This infinite, branching multiverse is a breathtaking vision, but it is built upon a foundation we still do not fully understand. The very mechanism that spawns new universes, quantum tunneling at the cosmic scale, remains the greatest unsolved puzzle in all of physics. This brings us to Theory 28, which frames the universe's first quantum leap not just as a historical event, but as the ultimate laboratory for a final theory of everything. That first tunnel is the Rosetta Stone for quantum gravity. For over a century, physics has been split into two magnificent but incompatible kingdoms. On one side stands quantum mechanics, the rulebook for the impossibly small. It governs particles, probabilities, and the fuzzy uncertainty of the subatomic world. On the other side stands Einstein's general relativity, the master theory of the immensely large. It describes gravity as the curvature of space-time by mass and energy, dictating the motion of planets and the expansion of the cosmos. Both theories are spectacularly successful in their own domains, but they violently disagree about what happens when the realms collide, when immense gravity is packed into a microscopic space. This is the regime of the Big Bang, the interior of a black hole, and the moment of our universe's quantum birth. At that singular instant, both quantum weirdness and gravitational fury were supreme. To describe how a universe could tunnel from nothing, we need a theory that seamlessly blends the two, a theory of quantum gravity, and the probability of that first tunnel is its most critical test. Think of it as the universe's own birth certificate. Any candidate for a final theory, be it string theory, loop quantum gravity, causal set theory, or something yet undiscovered, must be able to do one very specific, very difficult thing. It must calculate from first principles the likelihood that our particular cosmos would quantum tunnel into existence. This is not an abstract exercise, it is the ultimate benchmark. The equations of a true theory of quantum gravity would contain within their mathematics a description of the instanton, that timeless bridge from nothing to something. They would define the landscape of possibilities and show the precise pathway our universe took. Most importantly, they would spit out a number, the probability of our specific universe appearing. This number would be the theory's grand prediction, a single figure encoding the origin of all reality. The search for this probability is what drives physicists to the edges of mathematical possibility. In string theory, they compute it by summing over all possible histories of vibrating strings in higher dimensions. In loop quantum gravity, they look for it in the quantum transitions between discrete grains of space. Each framework approaches the problem from a different angle, like investigators trying to reconstruct a single, perfect sound from scattered echoes. The stakes could not be higher. If a theory successfully predicts a probability that aligns with what we can infer from our universe's observed properties, it would be a triumph of human understanding unlike any other. It would mean we have found the language in which the cosmos wrote its own beginning. This quest unifies the most ambitious threads of modern physics. The hunt for dark energy, the mapping of the cosmic microwave background, the study of black hole thermodynamics, all these pursuits feed into constraining that one magical number. They are gathering clues about the adult universe to reverse engineer its infancy. By understanding the universe we have, we inch closer to calculating the odds of it ever being. In this light, the first quantum tunnel is more than a moment in the past. It is an active, pressing question, a siren call to a deeper truth. The entire edifice of our reality hinges on a calculation we have not yet completed, a probability waiting to be found in the harmony between the very small and the very large. That ultimate calculation, the probability of our universe, may one day be written in a textbook, but numbers cannot answer the deeper whisper that has haunted humanity since we first looked at the stars. Why is there something rather than nothing at all? Every theory of quantum tunneling from nothing brings us face to face with this ancient, aching question. Science offers us a breathtaking how, a possible mechanism for the leap from non-existence to existence. But does it truly explain the why, or does it simply push the mystery one step further back into the shadows? When we say the universe tunneled from a quantum vacuum, we are describing a state of pure potential, a seething sea of probabilities governed by mathematical laws. But where do those laws come from? Why is there a quantum vacuum at all, with its specific rules that allow for tunneling? The scientific answer might be that those laws are eternal, self-contained, and require no further cause. They just are. The universe, in this view, is its own reason for being. It tunneled into existence because the mathematics of reality permitted it, a self-starting engine with no need for an external ignition. For some, this is a profoundly satisfying answer. It completes the picture within nature itself, refusing to invoke anything outside the system we can observe and test. It suggests reality is fundamentally rational, governed by logic that we, as products of that reality, can eventually comprehend. The why dissolves into the how, and the question of a first cause is revealed as a trick of language, born from our linear experience of time within the cosmos, not applicable to the cosmos as a whole. For others, this feels like a magnificent evasion. To say the laws of physics are eternal and uncaused is to state a brute fact, not an explanation. It replaces the mystery of existence with the mystery of eternal mathematical truth. Why this particular set of laws, one that allows for stars, planets, and life? If we accept a quantum tunnel from a pre-existing meta-universe, we must then ask where that meta-universe came from. Each answer seems to point to a deeper, more fundamental layer, an infinite regression of cosmic turtles all the way down. This is where philosophy and physics meet in a silent, staring contest. Some philosophers argue that a self-contained, uncaused origin is the only kind of origin that makes logical sense. Anything that causes the universe must itself be part of a broader reality, restarting the question. Therefore, the universe must be its own ground, a necessary existence. Quantum tunneling from nothing, in this reading, is the physical expression of that logical necessity. Others find this deeply perplexing, even unsettling. It feels like the universe is performing a magic trick, pulling itself out of a hat that did not exist until the trick began. The human mind, wired for cause and effect, rebels at the idea of an absolute beginning with no prior context. We crave a story that starts somewhere with something. Yet the scientific models suggest the story starts with a leap, not a thing. This tension may never be fully resolved. It lives in the gap between our deepest intuition and the universe's apparent logic. Perhaps the true value of these theories is not that they provide a final, comforting answer to the why, but that they transform the question itself. They teach us that nothing is not an empty box, but a realm of potent potential. They show us that cause may be a concept that emerges within the universe, not something that applies to the universe. In doing so, they do not silence the ancient whisper. Instead, they give it a new, more precise echo. We are left not with an answer, but with a clearer understanding of the magnificent mystery we are part of. The universe did not arise from a place we can easily picture. It arose from a possibility we are only beginning to mathematically describe. And in that description, we find not an end to wonder, but its infinite beginning. That ancient whisper of why may never be fully silenced, but science demands something more tangible. It demands evidence. After exploring 29 breathtaking theories, we arrive at the 30th and final idea, one that grounds our cosmic speculation in the hard, hopeful light of future discovery. How could we ever test whether our universe truly quantum-tunneled into being? The answer lies not in philosophy, but in the faint, frozen fingerprints the event may have left on reality itself. The first and most promising place to look is the cosmic microwave background, the afterglow of the Big Bang. This ancient light bathing the entire universe is a snapshot of the cosmos when it was just 380,000 years old. But we are not just looking for a temperature map anymore. The key signature may be hidden in the light's polarization, the specific direction its waves vibrate. A universe born from a specific type of quantum tunnel, particularly one involving gravitational waves in the earliest moments, would have imprinted a unique, swirling pattern called primordial B-mode polarization onto this light. It is a ghostly signature of space-time itself being wrung out by the violent birth pangs of inflation, which was likely triggered by the tunnel. Experiments like the Simons Observatory and future space telescopes are hunting for this pattern with incredible precision. Finding it would be like discovering the cosmic equivalent of a birth certificate, with the cause of birth listed as a quantum gravitational fluctuation. Beyond the whisper of ancient light, we might listen for the echoes of creation itself. The moment of tunneling and the inflationary expansion that followed would have generated a storm of gravitational waves, ripples in the fabric of space-time. Unlike the polarized light, these waves from the very first instance would have a much lower frequency, forming a stochastic gravitational wave background that hums through the cosmos like the deep bass note of the Big Bang. New observatories are coming online to tune into this cosmic symphony. Space-based detectors like the Laser Interferometer Space Antenna, or LISA, will listen for these waves by monitoring the precise distances between floating cubes millions of miles apart. If they detect a background with a specific spectrum, it could tell us about the energy scale of the tunnel, revealing the height of the barrier our universe leapt over to exist. Finally, the answers might not come from looking out at the cosmos, but from looking inward at the smallest pieces of reality. Particle colliders like the Large Hadron Collider are, in a very real sense, time machines. By smashing particles together at nearly the speed of light, They recreate conditions that have not existed since a fraction of a second after the Big Bang. Any theory of quantum tunneling from nothing must connect to the particles and forces that govern our world. Discovering new particles, like those predicted by supersymmetry, could reveal the shape of the energy landscape that existed before the tunnel. Measuring the properties of the Higgs boson with even greater precision could tell us about the stability of our vacuum, hinting at whether we tunneled into this particular valley or are perhaps destined to tunnel out of it one day. A single, unexpected discovery in a detector deep underground could provide the missing piece that makes the mathematics of a cosmic instant and click into place. These theories of our quantum origin are currently beyond the realm of direct proof, residing in the domain of elegant mathematics and profound speculation. But they are not untestable fairy tales. They make concrete predictions about the universe we should see if they are true. The evidence is not lost to time. It is potentially encoded in the polarization of the oldest light, in the faint rumble of gravitational waves, and in the behavior of particles at energies we are only beginning to master. The story of our beginning is not a closed book. It is a manuscript, and its final chapters are being written now in the data streams of telescopes and colliders around the world. The universe's first quantum leap may have been a silent, solitary event, but its echo might still be ringing all around us, waiting for the right instrument and the right mind to finally hear it. The journey through these 30 ideas is more than a tour of cosmic possibilities. It is a map of the human mind reaching for the edges of reality. We began with a universe tunneling from pure nothingness, a leap from a state of zero volume and timeless potential. We saw it reborn in endless cycles as a bubble in a meta-cosmic sea, or as the interior of a black hole in a forgotten parent cosmos. We explored how the arrow of time, the weakness of gravity, and the very structure of space might all be frozen relics of that first quantum decision. Each theory, from the holographic projection to the causal set, offers a different lens on the same staggering event, a moment when probability crystallized into history. Underlying every one of these visions is a single, profound shift in understanding. Quantum mechanics dismantles our most basic intuition about beginnings. In the quantum realm, something can come from nothing because nothing is not an empty void, but a realm of fertile potential. And something can appear without a prior cause because the chain of causality itself may be a product of the universe, not its prerequisite. The haunting question of what came before the Big Bang may be a question without a frame, like asking what is north of the North Pole. There may be no before, only a timeless probability that finally tipped into our reality. This is not a dismissal of the mystery, but its ultimate magnification. It suggests the cosmos is not a clockwork mechanism with a starting wind, but a self-starting flame, igniting in the silent dark through a rule that allows existence to bootstrap itself into being. That we can even conceive of such ideas, that we can weave mathematics and imagination into stories of cosmic birth, is a testament to an unquenchable curiosity. For thousands of years, we looked to the stars and told myths of gods and giants shaping the world. Today, we look at the same sky and tell stories of instantons and vacuum decay, of fields tunneling through barriers in landscapes of imaginary time. The scale of the question has not diminished, but the nature of our answers has transformed, grounded in the relentless collective pursuit of evidence. We are the universe becoming conscious of itself, using the laws born in a quantum leap to trace our way back to the moment of that leap. So, as this exploration ends, the conversation is just beginning. Which of these 30 doors into reality resonated most deeply with you? Was it the elegant simplicity of a universe from nothing, the cosmic genealogy of black hole births, or the infinite cycles of conformal eons? Share your favorite theory or a wild idea of your own in the comments below. The next great thought about our origins might not come from a lab or a telescope, but from a curious mind inspired by the greatest story ever told, the story of how all